Hello, I'm Hannah Sachs, Editor-in-Chief of NEJM Evidence, and this is Stat.
After a long week in the hospital, Saturday has arrived and it's movie night. A rom-com would be perfect to end the week on a lighter note. Or maybe an action pick. You search new streaming releases and start reading reviews. Some reviews provide a rating on a 5-star scale. Some use a scale from 0 to 100 tomatoes, and another one provides no score at all and simply waxes poetic about the film. At last, you find a single website that synthesizes all the reviews and summarizes an overall score from 0 to 10. This site makes it easy to find a movie you'll enjoy, and as you're scrolling through, you think, this synthesis resembles a meta-analysis. And guess what? You're right. Meta-analysis is a statistical technique that pools results across studies. For example, aggregating results of multiple movie reviews gives you a better sense of how reviewers in general felt about a film or the types of movies that are likely to be reviewed favorably. In clinical research, one use of meta-analysis is to pool results across trials to estimate the strength of an association between an intervention, say a medication for heart failure, and an outcome, say hospitalization for heart failure. A meta-analysis is not a randomized trial. It's an observational study of studies. Let's look at 5 key components involved in conducting a meta-analysis. First, you systematically search for studies, and of course there needs to be at least 2. Investigators typically review all relevant databases using a well-defined search strategy. Such a systematic approach seeks to avoid bias by including all relevant publications. Second, you consider the design of the studies. For example, you might have 3 randomized trials, 1 case control study, and 1 cohort study. While there are methods to combine different types of studies, doing so complicates the analysis and is less common in clinical research than combining studies of a single design, such as randomized trials. Third, you want trials to have similar patient populations. Defining similar can be subjective, but you can imagine that combining results of a trial of an intervention among older adults with another that included only infants is unlikely to be informative for adults. Fourth, the studies need to be evaluating the same intervention. And fifth, the studies need to have the same, or again, similar outcome definitions. For example, all the movie reviews have the same outcome, movie quality, even though many use different scales. Let's work through an example. You conduct a review of the literature on a specific medication in heart failure and identify 3 RCTs that tested the effect of the medication among adults with heart failure with reduced ejection fraction on heart failure hospitalization. 2 of the 3 trials suggested that the medication had no effect, and 1 suggested that it decreased heart failure hospitalizations. Pooling the results should allow you to estimate the average effect. But how? Can you simply add up the 3 relative risks and divide by 3? Well, while that's one approach, it doesn't feel right. Doing so implicitly gives the same weight to each trial, but 2 of the trials were tiny, and 1 was large. One common approach in clinical research gives more weight to trials that have results with tighter confidence intervals, that is, less variance, and less weight to trials with wider confidence intervals, or more variance. Of course, there's also more to consider. Investigators decide whether to employ what's called a fixed effect or random effects analysis. A fixed effects approach assumes that the underlying treatment effect is the same in all trials, and differences are due only to sampling error. That assumption is rarely true in medicine, where trial results are often heterogeneous for reasons other than just sampling. For example, trials you identified may have a lot of unmeasured between-trial heterogeneity, say characteristics of the patients or of the health systems where the trials are conducted, all of which could impact the magnitude of an intervention's effect. For that reason, most meta-analyses of RCTs use a random effects approach, which assumes there is between-trial heterogeneity in the underlying treatment effect. So, now that you get the basics, you're ready to jump in. You refine your systematic review strategy, identify 13 RCTs, and employ a random effects approach. You display your results in what's called a forest plot. Each horizontal line represents the results of an individual trial. The length of the line is the confidence interval, and the diamond is the pooled estimate of all the trials. The width of the diamond represents the 95% confidence interval around the pooled estimate. All this stats talk is making you tired, and it's almost movie time. The key point is that meta-analysis pools results from multiple studies to learn more than can be learned from a single one. And like in a meta-analysis, the pooled result from multiple movie reviews gives you more confidence in your movie night choice. Simple enough. Time to enjoy the show.